Now welcome back. This is lecture 29. Last couple of lectures we have been discussing about layouts of passives uh, at a very top level, right? Once you start designing, you are going to see that the models that we discussed are quite simplistic, and obviously the simulator and the PDK that you are going to use, or the process design kit that you are going to use, are going to give you better models. But the whole purpose of the last two lectures was to give you an intuition as to what are the things that you need to look out for when you want to optimize a passive device, right? And for example, when you are trying to optimize a capacitor, how do you go about reducing a loss? What are the loss mechanisms in an inductor? How do you go about optimizing the layout of an inductor for RF frequencies, and so on and so forth, right? So in today's lecture, what we're going to do is to see what happens if we have, how does a circuit performance get impacted if we have losses in our LC circuits. And we'll also start to go into some analysis as to how to go about thinking about these losses with regards to the impact they have on your overall design, right? So the agenda of today's lecture is to start formalizing these effects of parasitics from the standpoint of a circuit designer, right? Okay. So before we start, some definitions. I'm sure all of you also are aware of this definition in some sense or the other, or will have an intuitive feel of these definitions. But it's better to, when we are going into doing something analytic, it's better to formalize those definitions, right? So the first definition that we are going to look at is called a Q factor, or a quality factor of an inductor. So as the name mentions, so if you have an inductor, and let's say I have a loss in the inductor, and I model this loss as a lumped R, right? Now you might say that we have so many loss mechanisms, how can I model it as a lumped R, right? In principle you cannot, but let's assume that at a particular frequency I characterize the inductor, right? At a particular frequency I got some inductance and I got some loss. So at that particular frequency I am lumping that loss as a series R. And at that frequency, whatever the effective J omega times whatever I got is the inductor, right? So if we stick to that definition, then this at a particular frequency, this model will kind of be valid, right? So let's assume that. So if I assume that, then this is L, this is R, right? So similarly, we can have a loss mechanism in a capacitor, but we'll stick to the inductor for the time being, because inductors are at the RF frequencies that we are mostly interested in. Inductors are the most lossy components. Okay, so the first definition is that of a quality factor, or a Q factor, which is almost always referred to as Q. Okay, so how do you know if an inductor has a good quality with respect to one inductor is better in quality than the other? The only thing to look for is what is the amount of loss. Now only looking at loss is not sufficient. We have to look at, with respect to the value of the inductance, how much is the loss, right? You would expect absolute value of loss doesn't really make sense, right? Because if I am expecting an inductor which is this large, as compared to an inductor that is this small, then obviously I can tolerate probably more amount of loss in the bigger inductor than the smaller inductor, right? So in the more formal definition of Q factor, therefore, has to do with the stored energy, because inductor is essentially in this case storing the energy, and R is dissipating the energy. So if you have a contraption which I know is supposed to be an inductor, and I know that there is certain amount of power dissipation where there is supposed to be none, then the amount of power dissipation with respect to the amount of stored energy is kind of a metric of the quality, right? So, or in other words, if I take the ratio of the stored energy divided by the dissipated energy, right, higher the better, right? Okay, so the formal definition is peak energy stored per cycle divided by power dissipated. So energy stored per cycle has kind of units of power, and the ratio of this divided to the power dissipated, and there is a factor 2 pi, right? So because this 2 pi, we will soon see why this 2 pi has been brought into picture, just to simplify the overall the expression of Q. But I mean, having the 2 pi or not having the 2 pi doesn't really make too much of a difference with respect to the definition of, with respect to the intuition of what a Q factor should be, right? Naturally, we expect the power loss, or in this case, if we take an inductor, we expect the power dissipated, that is the loss due to the series R, should be much smaller than the power, the energy stored per cycle, right? So if I have a if I do it in time domain, right? So let's say I have a sinusoidal current at a frequency omega, and that current is IT is equal to I max sine omega t. So therefore Q factor is essentially 2 pi times what is the energy stored in the inductor. Actually, ideally the definition is peak energy stored in the inductor. So this is the peak energy stored in the inductor. So this is half Li squared of half L times I max squared per cycle, right? So which essentially I have to divide by the time period, right? Or multiply by F, multiplied by F divided by the power dissipated. Now what is the power dissipated? It's basically current going through R, so is I max sine omega t. So power dissipated is half I max squared times R. So this goes off, this goes off, right? 2 pi times F is omega, so this becomes omega L over R. So essentially the Q factor, which by the way is also a function of omega, right? The Q factor is omega L over R, right? So this should be also intuitive, because what is this telling us? It is basically telling us that if I want a good inductor, I would want that R to be as small as possible with respect to omega times L, right? Ideally a Q factor should have infinite Q, because ideally we do not want, ideal inductor should have a Q factor of infinite, because we do not want any loss. So R should be ideally be 0. So that also checks out. Okay. The other thing that is telling us is that it looks like the Q factor of the inductor becomes better as we increase frequency, right? So why? Because the impedance offered by the inductor is increasing with respect to the loss that we are having. Now you might want to stop me here and say that, hey, this R that I have put here is also not frequency independent, right? So this R has skin effect, proximity effect, and all those other things, which is also frequency dependent, and you will be absolutely correct. But through the 0th order, right, till the frequency at which those skin effect and proximity effects and everything don't start to dominate, at least I can say that my inductor my inductor has will behave better, will have a better quality factor at higher frequencies. And that is what we also saw without really defining a Q factor. If you recall, we saw some plots of imaginary part and real part and the loss, and when there is a self-resonant frequency, and then before that we saw where at what frequencies we'll have a peak value of the imaginary part, and then there will be a loss, and so on, right? All this is telling you is that once you get an inductor, you plot its Q, right, and then see where the Q factor peaks. So eventually you are going to see because if you use a real inductor, you will see that the Q never goes high up and up and up. It will eventually also go down, right? So wherever you have the peak is probably the best place to operate your inductor. And when you are designing your inductor for a particular frequency, you have to ensure that around that frequency you kind of get the peak of the Q. Okay, so this is a formal definition of Q. There is this definition of Q factor is always valid. So this is the mother definition of a Q factor. Okay, this is always valid. Now there are some approximations of this Q factor expressions, or rather some specific cases of Q factor expressions, which are, so if we have only LR or RC circuits, not LRC, only LR or RC circuits, then this is, let's say I take the example of an LR circuit, then, and I drive it with a voltage source, I drive it with a voltage source or a current source, it doesn't matter. So what is the power dissipated here? Power dissipated, this we have done in the context of finding out the noise spectral density, right? So power dissipated is essentially the real part of the impedance that we see, right? So this is the real part of Zin. So if this is Zin, the real part of Zin. And what is the power that is stored, right? The power stored is imaginary part of Zin, right? So if you have an only LR or RC network, then the definition of the Q can also be written as imaginary part of Zin by real part of Zin, right? So if I mean this should be readily understandable if you take the same example of our inductor with lossy inductor. So what is Zin? Zin is j omega L plus R. Therefore Q is omega L over R. Okay. So be mindful of the fact that if you have a resonant circuit inside, that is, if you have let's say an L and a C also, then it is possible that the imaginary parts cancel off, right? So that's why these that is the intuitive way of saying that this definition does not hold true when you have LRC circuits. It's true for when you have only LR or RC circuits. Okay, but this is also a very useful definition because it kind of gives us a idea about how to think about quality of a component. Similarly, if I have a RC network, let's say I have a R and a C, or rather a C which has a series R, correct? So what will be the quality factor of this guy? So again, I can go by either of this energy stored by and power dissipated, or I can go by the real part and the imaginary part. So imaginary part of this impedance is 1 by omega C, right? And the real part is R. So this is 1 by omega RC, correct? Okay. So once you have an expression, you should again readily question yourself whether it makes sense or not. So how do you know whether it makes sense or not? So if R is 0, what do you expect the quality factor to be? Ideally, you do not expect any R to be there. So you should have infinite quality factor if R is set to 0 in this case, right? So does it make sense? Yeah, it makes sense. So 1 over omega RC. Now the thing is, with 1 R, 1 C, or 1 R on 1 L, you can have series or parallel combinations of R and L and R and C, right? So do you think quality factor expression will change? The definition doesn't change, but do you think the quality factor expression will change? Let's see, right? So let's say I say that instead of doing this, I say there is the network is C and R, and this is the network, right? So even without solving for it, do you have an intuition as to whether in the quality factor expression of this network, the R will come in the numerator or in the denominator? So the way to think about it is, again, is for an ideal network, in this case, ideal in the sense that I want the C to be pristine, right? No loss. So in this case, then R should be what? R should be infinite. R cannot be 0. If R is 0, then the C is bypassed totally, right? So I expect R to be in the numerator, right? So that is that even without solving, I can get an intuition, right? So, but if I solve for this, what do I get? What is Z in? Z in is 1 over R plus j omega C, right? So basically R by 1 plus j omega R C, and if I do the real part imaginary part thing, so this will be R times 1 minus j omega R C, right, divided by 1 plus omega square R square C square, which effectively means that your Q factor is, the imaginary part is omega RC and real part is 1, right? The other ones get cancelled out, right? So because this is common, so this part is common, so don't have to bother. So your Q factor is omega RC. I mean, don't bother with the negative sign. Q is always 1, so it's basically the energy, right? You take the mod, right? So these are all approximations, or rather a cut down expression of what the energy stored and energy dissipated are, right? So note that energy dissipated is always positive, right? But the expression of energy stored, you can have a plus j, minus j, depending upon whether the current is leading, lagging, and so on, right? So so you can have, don't bother about the negative j part of the energy stored. Okay, so this becomes Q equal to omega RC. Now, without going into solving, can you tell me what will be the Q factor of this guy? Of this network? So when R was in series, it was omega L over R, because I wanted R to be 0, right? When R is in parallel, what do you want R to be? R to be infinite. So your Q factor will naturally become R by omega L. Why not R omega L? Because note that Q factor has does not have any unit, right? So another thing to mention is that Q is unitless, and Q is also frequency dependent, right? So these are the two things also you should keep in mind all the time. Okay, so the next thing to consider is how does this impact our circuit operation, right? So note that when we are doing LNAs, right, we assume there is a resonant load and so on, right? So if you to refresh your memory, so one example that we do it was, if you have an LNA and maybe you have this source degenerated LNA, and we said that we are going to have a resonant load. This load kind of gives you infinite gain at the resonant frequency, but I also understand there is an RDS here, so the gain will not go to infinite, but we assume that the inductor is ideal, right? But I know that the inductor, neither the inductor nor the capacitor can be ideal, because there are resistances associated with each of these elements. So how does the performance of this tank get affected if I put a lossy element alongside it, right? So now what we'll do is, at the RF frequencies, like if you are not crossing like a few gigahertz, if you are well below 10 gigahertz frequency range, then as it turns out, the loss due to inductor always dominates. I mean, that should make sense to some extent, because if you assume there is a series resistance with respect to series resistance with the inductor, then obviously omega L at lower gigahertz frequencies or at low frequencies will not be the ratio of omega L over R will reduce at low frequency than at high frequency, right? So, but it's unlike a capacitor where it's omega 1 by omega RC, where the Q factor is better at lower frequencies than in higher frequencies. I'm talking about series resistances, right? So the next order of business is to find out what happens if I have this scenario. What happens if my inductor has a resistance associated with it? The inductor in the tank has a resistance associated with it. Right? So what is Zin at resonance? So clearly Zin is not infinite at resonance, that I know, because it's not an L and C in parallel, right? And also there is an R, right? So how do I go about solving this? One way to solve this brute force, I find out Zin for this and set the imaginary part to 0, and whatever I get is the resonance, right? Is the impedance at resonance. But even though the analysis is correct, but it doesn't really give us an intuition. What I would like to have is an intuition, a feel behind what the impedance will be, and also have a design feel behind why. What should I do in order to estimate the impact of this R on both the resonant frequency and the overall performance of the system, right? So to do that, ultimately I would like to express this. So at some frequency, so at a single omega, if I can express this thing as some R equivalent at some omega, I'll just write R equivalent for the time being, and maybe I will have some L equivalent, and this capacitor, let's say, remains capacitor, right? So, or in other words, if I can express this this guy and L as an R equivalent and an L equivalent in parallel, then if I put the value of capacitor across, then if I put this capacitor here, then I know that I will be able to resonate out the L equivalent and the C, and will be left with R equivalent, right? So that's the whole purpose of trying to express this series connection of L and R into a parallel correction of L and R. So firstly, I don't even know whether it will be an L when I transform it in a parallel network. I mean, I know a priori, but we'll see whether what happens, right? So what should be the way of going about doing it? So let's see. So if these two networks, if this and this have to be equivalent, right? So then what should I match? I should essentially see the input impedance here should be the same as input impedance here, right? Or since I want to transform this series into parallels, maybe it's better to look at the admittance, because maybe the algebra will be simpler, right? So let's look at the admittance. So what is the admittance? Y is basically 1 by R plus j omega L, which is R minus j omega L by R square plus omega square L square, right? Which I can break it up as R by R square plus omega square L square minus j omega L by R square plus omega square L square, right? Now this clearly is a resistor. What is this? Note that I have minus j, negative j, which means this is in the admittance, right? So if you are not convinced, you can think of this as plus j 1 over j times this, and the value of the inductance will be basically R square plus omega square L square by omega L, right? It is at a particular frequency. The value of the inductor will, whatever this component will be, will also change, but we are not bothered about that for the time being. We are bothered about a single frequency, right? Okay, so let's proceed. Now what I will do is I will try to replace these terms with the Q factor, right? So given that I know that Q of the inductor, where R is in series with L, is omega L by R, that is, I can express omega L to be equal to Q times R, or I can also express R to be equal to omega L by Q. Now, depending upon which makes the point, I'm going to use that thing. So then y is essentially r by r square plus omega square L square is q square r square. Again, I will remind you, is q is a function of frequency, right? Just because I'm not writing q omega, it doesn't mean that q is independent of omega. Okay, and this I will write in the inductor term. What I will do, I will express the r in terms of omega L and q. So this becomes 1 by j omega L by omega square L square over q square plus omega square L square, right? So this becomes 1 by r 1 plus q squared plus 1 by j omega L 1 by q squared plus 1, correct? So what does it look like? Admittances getting added up, which means things are in parallel, and this is basically a resistor of value 1 plus r times 1 plus q squared, right? So this is resistance of value r times 1 by q squared, and this is an inductance of value omega L times 1 plus 1 by q squared, right? So this is an inductance of value L times 1 plus 1 by q squared, right? Okay, so this becomes the equivalent Zin. This is a series to parallel conversion of this network, right? So this Zin at a frequency omega will be identical to this Zin at the same frequency omega, where q is equal to omega L by r. Okay. Okay. So now there are two aspects to it. Rather, there are two consequences to it. So note that ultimately we wanted to put a capacitor to resonate the imaginary part out. So I will put a capacitor to resonate the imaginary part out. So now at what frequency the resonance is happening? Is it happening at the if I put a value of capacitor C, this is C on the do you think the resonant frequency is 1 over under root LC? In the absence of R, the resonant frequency was 1 over under root LC. Is the resonant frequency 1 over under root LC? Clearly not, right? So what will be the resonant frequency here? So your resonant frequency omega naught, or omega naught square, is 1 over L, where L 1 plus 1 over q squared is r square by omega naught square L squared times C, right? So once you solve it, you are going to get the value of omega naught to be 1 over under root LC times square root of 1 plus r square C over L, or rather 1 minus r square C over L. 1 minus r squared C over L, right? Okay, so the key thing, first thing to note is that there is a shift of center frequency. Your center frequency kind of goes to a lower frequency, but as long as your r, this value, this r squared C over L is much greater than less than 1, you can kind of neglect that shift. And as it turns out, unless we have done a very lousy job of making an inductor, this shift for most practical situations is not significant, right? But it is good to know that there is a frequency shift. And why did I say that in most practical situations it's not a problem? It's because, now note that at a very intuitive level, what is this R causing? This R is causing a change in the effective value of this inductance, right? If Q is much greater than 1, right? Or rather, if Q is much greater than 1, if Q is much greater than 1, then this effective L equivalent is almost equal to L. Right? So in that case, there is no frequency shift. Ultimately, the goal is to make a very good inductor, right? We would like to have a Q to be much greater than 1, right? So which essentially means that in most cases you would be fine while assuming that there is no resonant frequency shift, right? So that is number one, right? And what is a more important thing? At resonance, what is happening? At resonance, omega naught, that is resonance, right? At resonance, this gets transformed to a resistor, right? Because this L and C are going to resonate out, and the resistor of value, original value of R times 1 plus Q squared, which I can approximate it to be R times Q squared if Q is much greater than 1, right? And for example, if the Q is, for example, 10, then 1 plus 100 or simply 100 doesn't really make too much of a difference, right? So you can see that it looks like there is an amplification of this R, right, at resonance, which should make kind of sense, right? Because for example, if R is 0, right, if R is 0, then what do you expect? What do you expect the Q to be? If R is 0, the Q has to be infinite. So ultimately, when R is 0, this looking in impedance should go to infinite, and that's what is actually happening. Just note that again, Q is omega L over R, right? So Q is also, so if I write it out, this becomes R times omega square L square by R square. So this is omega square L square by R, right? So at resonance, your input frequency impedance also increases, right? Okay, so two things, right? So once you transform these series into parallel and you resonate out the imaginary part, you are kind of, two things are happening. There is a slight shift of center frequency, which might not be too much of a concern unless your Q is very bad. And but the more important thing is that you have an amplification of that R. The lossy R, right? The effective lossy R is now getting amplified by Q square, right, and getting presented as the effective load, right? So now in that case of your LNA, where you had this scenario, so this I can, at resonance, I can basically say it looks like this. It's R times Q squared, right, which effectively gives you offers the load, right, in parallel to whatever load was already existing. What about noise from this R? Do you think just because obviously the RV is going to give you noise, but do you think just because the value of the R is getting multiplied, the noise will also get multiplied? No, right? Because this is a modeled R, right? So intuitive example is, if R were not there, you get infinite impedance. That does not mean that you get infinite noise also, right? So noise contribution from that R, right? So this is good because you can kind of use this resonant circuit even in the presence of some lossy R to get decent amount of amplification if necessary, right, when used in this configuration. Now note that there is an interesting part to it. It looks like this. If I now redraw this thing, let's say redraw this thing like this, let's say the same thing I redraw like, now I'm changing the context, right? So this is, that was a separate discussion. Now this is again a discussion using RLLC, but the context has changed. So let's say now I say that instead of representing it like this, I am going to represent it like this. And I'm going to say that this is a two-port network, and this is some R1, this is some L, this is some C. Okay, more. And if I say that I do not know, let's say I give an user a box. Inside the box I don't know what is there. The user doesn't know what is there inside the box, and there is an R1 here, right? So this stuff is inside the box, right? So the user doesn't know what is there inside the box. So what will the user feel? And let's say the user is using it at the particular frequency omega naught, right? At the resonant frequency omega naught, right? You would have not told the user what is inside the box, but you have told the user that you know what the resonant frequency is a priori, and you tell the user that operate this at resonant frequency at this particular frequency. The user puts an R1 at this side at port 2. At port 2, the user puts a R1 on this side. What will the user see on this side? The user will see R1 times Q square, which is much greater than R1. So to the user, it would look like this looks like an impedance transformer, right? There is a transformation of impedance, right? So as far as the user is concerned, if you tell the user do not change the frequency, at this frequency only you are going to use, what will the user feel? You will feel that this is a transformer, an ideal transformer, right, which has transformed the impedance from R1 to a value R1 times Q squared, right? So which means that it is a n is to 1 transformer where n is equal to Q, correct? I mean, the reasoning behind the transformer, let me give you a 2-minute refresher. So let's assume that this is a transformer refresher. Let's assume that you have an ideal transformer of 1:n turns ratio, correct? And there is some load connected on either side, right? So let's assume that there is a load RL connected here, and you are applying a voltage here. I would like to find out what is the impedance looking in. That is the goal, right? So what do I know? If this is V test, if it is 1:n, right, what will be the voltage across this this secondary port? So this will be n times V test, right? Let me call this V1, and let me call this I1, let me call this V2, and let me call this one I2, okay? So I know that this is, if it's an ideal transformer, fully passive, no loss, then I know that the power going in should be the power going out, right? So I know that I1 V1 should be equal to I2 V2, correct? So what is I1? I1 is essentially I test. What is V1? V1 is V test. What is I2? I2 is n times V test over RL. What is V2? This is n times V test. So essentially I know that I test is equal to n squared times V test over RL, which means that V test over I test, which is basically the Zin, which is equal to RL over n squared, correct? And now compare to this situation where, so it looks like if we have a trans ratio of 1:n, right, the primary is 1, secondary is n, the effective impedance gets transformed to RL over n squared. In this case, the effective impedance is increased to R1 times Q square. So then the trans ratio should be other way around. It's basically Q:1, right? To the unbeknownst user who doesn't know what is inside and is using it, he or she is using it at a particular frequency, we see that this will be equal to, it looks like an impedance transformer of value where the transformer has a value of Q, right? Now the question is why? What is the intuition behind this, right? That is what we are going to see next. So let's now look at the intuition behind how to think about this impedance transformation, right? So So clearly the impedance transformation is happening because of what? Let's say I have a two-port network and let's say this is lossless. This is crucial. If this is lossy, then this analysis doesn't hold. This is lossless and you have current that is I1 and voltage that is V1. And if the voltage, somehow the voltage V2 is V1 by N, that is, I step the voltage down by factor N, then what do you think? I mean, obviously there some load is connected. Without that load connected, nothing is going to happen. What do you think this current will be? What do you think this I2 will be? How do I know what this I2 will be? This I2 net, because this network inside is lossless, I know that I1 V1 has to be equal to I2 V2, right? So which means this I2 will naturally be V1 I1 V1 divided by V1 over N, means multiplied by N, which means I1 times N. Correct? So moment you express in this format, which means that your, so now similarly if I now express things in terms of I2 with respect to I1, right? So which essentially means that the power delivered is, if this is RL, which means power delivered here is V2 times I2, which is V1 by N times I1N is equal to I V squared by RL, right? So which means this is I1 times N whole squared by RL. This goes, which means P1 equal to I1 times N squared by RL. Sorry, this is times RL square over RL, right? So this is N squared times RL, which means your V1 over I1 becomes N squared times RL. Correct? So the thing that you have to look out for here is the fact that if you have a lossless network and you have a step down in voltage, right, then the resistance at the port 2 increases by a factor of the step down ratio squared, right? So that's the key thing to note, right? So the key thing to note is that for impedance transformation, we need a lossless network, and number 2, we need a step down or a step up of voltage, right? Step up or down of voltage. That's all we need. Now from the lens of, okay, so third thing is the impedance transformation ratio. Ratio is proportional to that N squared, right? That step up or step down whole square. Now depending upon whether it's multiplied by N square, divided by N square, it's based on whether you are stepping down the voltage or stepping up the voltage, right? So right now we are concentrating on stepping down the voltage. In the next lecture we'll give an example of stepping up the voltage, right? So now from the lens of this transformer, what do you think this looks like? What do you think this network looks like, where this is the box? So if you think about it, I can express this. I can assume that, let's say the capacitor doesn't exist or the capacitor is outside the box. I can say that this is like this is R, this is L, and I have a capacitor here. Okay. And if I look from here, what do I see? If I apply a test voltage here, if I apply a V test voltage here, what is the voltage across R? VR is basically R by R plus J omega L, And if we are operating at a frequency, so if omega L is much greater than R, right? Then I can basically say that VR is approximately equal to R by j omega L, right? Or basically 1 by jq, correct? VR over, I'm sorry, this is VR over V test. So your step down factor, right? Forget about the J term because we are interested in the mod, right? As I told you about Q factor when we are talking about, we are interested about the mod thing because ultimately it's all the powered equations that comes into picture. So your step down factor, right? Step down factor is equal to Q. So your voltage step down factor rather. So we expect the R to then get stepped up by Q squared, right? So which we already know because I know that RL is equivalent to L and R, which is Q squared times R. This is approximately L, this is C, correct? So at resonance this becomes R times Q squared, right? So hence looking from here, your Zin becomes R times Q squared, and hence your at resonance at omega naught or at resonance, this behaves like a transformer of turns ratio Q is to 1. Correct? Does that make sense? Okay. The thing that you should mindful of is, let's do another example, maybe that would help make the point. So what about this? What about now the stepping down? What did we do? We essentially stepped down the input voltage by the ratio of R and omega L, right? So this stepping down I can do with respect to C also, correct? So for example, I can do a step down with respect to C. There is nothing holy in keeping only an L. So this can be C, this can be R, right? So what will be the step down factor? So if this is V test, VR, so your VR over V test is R by, or rather R by R plus R 1 by j omega c, sorry. If you are operating at a frequency where 1 by omega c is much greater than R, that is omega is much less than 1 over RC. Note that in this case we were operating at omega much greater than right? Here we are operating at omega much greater than R, omega much greater than R by L. Here we are operating at omega much lesser than 1 over RC. Then you can basically say that your step down is happening. Your Q will be equal to, in other words, your VR over V test is essentially R times J times omega RC. So if you transform this into a transformer and resonate out, right? So if you resonate out with an inductor, right? If you resonate this out with an inductor, this should behave like a transformer of n is to 1, where n is equal to omega RC, right? So as long as omega is much greater less than RC. Okay, we'll stop here. Thank you.